I wanted for you to just, quickly, I'm going to just show you quickly the steps, okay, to consider environmental effects on the material stiffness. We saw a little bit of that this morning, right? Now I'm going to show you every single step we follow. And again, it's a mechanistic empirical method. That's how we do it in payment analysis. But I want you to know what the questions were, how we can get that one. And I want you to be curious about other methods or some other way to do it. But so here we go. We're going to be doing, maybe starting here. So we went today or yesterday, I don't remember, I think today, I told you, okay, we have different methods to estimate the climatic conditions in the prediction of the stiffness. One which was the effective stress approach that I told you I don't want to use that one. That's Bishop, right? And there are many literature with that. The second one is using the factor that takes into account the contribution of matrix suction independent of the traffic, right? That's the example that you saw this morning, right? And the third one is considering the resilient modulus a function of the complete stress state, that I show you the big equation with the Z1, Z2, Z3, Z4, or Z1, Z1, you said, but so we're going to be focusing on number 2, on this one. The factor that considers the contribution of the suction independently on the externally applied pressures. And you saw this one that I got from Plaxis. Okay? But you didn't see how I got this one. The only thing you get from Plaxis are going to be your suction profiles, which is going to give you those degrees of saturation profiles, okay? And then I briefly show you the equation to get the environmental factor, right? But in order to get there, okay, there are ways of doing empirically, more empirically, okay? Don't have to run Plaxis for that, all right? And this is what actually the AASHTO design guide, which is the latest design guide that we use, is the way that they're doing it. They're not running Plaxis, they're not running final element modeling, they're doing empirical modeling, okay? And I brought this one because I know we have the practitioners in here for railroads and also for payments. So this one is part of the model, the climatic model we put together for that design guide. And that was a word that we used to call MEPDG, the Mechanistic Empirical Payment Design Guide. And that's, again, the latest that AASHTO basically adopted as the latest payment design guide in the United States. And it's been implemented in every one of the states. Probably half of them have already been implemented that. Half of them still use the AASHTO 93 way. So I want to provide the input parameters for you to follow that climate model. Like again, it's empirical model, right? It's empirical, but it's based on mechanistic principles. I will provide you the models, and what you want to do is to follow this procedure to estimate the modulus for 2 different site conditions. Let's say, I'm going to give you that, and 2 different soil types, and see what we get. Okay, and see what we get. Then we can analyze from how to Friday, briefly analyze what you get. Okay, so we're going to divide the group, and you're going to do exactly the same thing, but you're going to be using different data, right? So we got all the information in here. So this is the model that counts for moisture and suction effects. And actually, it's very interesting to know that how many years, I think probably payment engineering was the first engineering that we had in the world, probably this one and water. We've been designing roads and building roads forever, right? Hundreds of years. And only until 2000 that we started incorporating the suction effects into the payment design analysis. So I'm talking to you that this is just right now, right? We did it before that was, very empirical factors here and there. Okay, so here are the steps. that I want you to follow. And this again is a prediction without using finite element modeling, without using the questions, all of these things. You're obviously going to need the climate, right? Because you're going to know what is the climate of the region. And again, I'm going to go pretty on top of it, and you're going to ask questions if you have. And you're going to have the groundwater table, and I'm going to tell you the groundwater table is a great depth, okay? At this point, this is soil that are subjected to. And basically, with this climate, we estimate the third wind moisture index. The third wind moisture index, I'm gonna go for that in a second, is a humidity or aridity index that represents the climatic conditions of a site. Okay? So instead of putting a boundary condition when you have infiltration, evaporation, when you're doing CW or Plaxis or any other program, we're gonna put a factor that represents the condition on that, right? And this one with soil properties, and that's your question in here. I'm gonna show you the model that we have, joining those together. We're gonna get the suction at equilibrium of a particular site. Okay, what I'm telling you is you're gonna have exactly the same soil here and in the desert in the Sahara. And the suction at equilibrium of the two soils will be different, right? Because of the environmental conditions that you have. All right? So the soil can be exactly the same pore size, the same, pore network, the same capillary. But if you have a different environmental condition, the suction at equilibrium is going to be in the graph in another place, right? In another place. Because it's going to try to get more water, because it's going to be always evaporation trying to get in here, or more infiltration, so it's going to have more water, and the suction will be different. All right? It's very easy. You got the saltwater characteristic curve, you understand that. With the matrix suction that you got at equilibrium condition, if you have always this, infiltration evaporation forever, or a long-term condition, you got this equilibrium condition for that site, okay? And if you have the saltwater characteristic curve, you can imply the moisture content. Now, to me, that will be enough to have this guy. Didn't go away, this guy. But pavement engineering do not use suction, okay? They use a surrogate and they use the moisture contents, right? Because this is easy for them to understand. He understands suction. This is easy for them to measure in the lab, and it's easy for them to, and this is being the norm, They don't want to talk about suction, okay? Fine, we got the saltwater characteristic curve, we gave them moisture content or degree of saturation, okay? With together, another question that we have today here from Ahmad, we use also freeze-thawing adjustments, and unfortunately, that's why I went for your answer, because I didn't have this in here. We use those two, and we calculate environmental factors. You're going to be calculating only the environmental factors for the frozen condition, right? But again, if we have freezing and thawing conditions, we need to make adjustments to this value. We're not going to go to that. Calculate environmental factor, okay, that now can be multiplied, right? Can be multiplied by the environment, by the optimum moisture content on that. And I'm going to be using a long-term condition, right? I'm going to give you one TMI that represents the value at equilibrium for that site. But I can give you also TMIs for every month to represent summers, to represent winters, right? So environmental factors actually can be varying with time if I give you factors every month. But this one that I'm giving you is kind of an annual condition, and it's going to be like that forever. Or, it's that site, that's the condition you get. And then actually you multiply this one by the optimum resilient modulus that you know how to get, and get the resilient modulus at equilibrium conditions. So the third wind moisture index, this is the guy that represents, this is actually the equation that we got for here. It seems to be simple, and it's not that simple. But again, it represents an annual index. This is precipitation and potential evaporation. Again, You got, it's a function of many parameters. I'm going to have you reading this thing, okay? But just to give you, it's a balance between the rainfall and the evaporation we have, all right? It's a balance of that. There are equations to calculate the potential the actual evapotranspiration. This is the difficult thing to get, all right? And there are equations available for that I'm not going to ask you to solve because it's going to take you 3 days to do the spreadsheet and solve it. So I'm going to give you the TMI already, okay? But the data is going to be available in here. These are the equations that we use. We need heat index, and again, you take 12 months for something like that. You can take 12 months in 1996 or 2025 or anything, or you can take from June to June in 2020 and 21, okay? So the TMI actually can be calculated monthly if you want to. And here are the questions. It depends on, there was a question yesterday. There is a daylight correction based on the latitude you have. So you need to be very careful because if you're using the design guide from the United States, this is for the northern hemisphere, okay? If you're gonna be using that in the southern hemisphere, you need to use, a table to do it by hand. And these are the tables for the northern hemisphere, and we have one for the south. But, the factors are, some of them might be a little bit higher, but some of the factors are not that high. But basically, you just get, the negative of the northern hemisphere. Yeah. These are some examples of the TMI, and I show you them this morning. Some of the Phoenix is minus 55, more evaporation than precipitation. Los Angeles is minus 32. So if you have negative, means that the balance is that during the year there is more evaporation than precipitation. Dallas is minus 2, so it's kind of in the balance, in the middle. This is Dallas, Texas. Miami plus 17, depends on the station you got. Orlando has, a little bit different number. Athens, Georgia, 33 plus 33. So positive means a lot of water in there. Negative means arid and semi-arid regions. Here are some data here for India that I found, these are the index for different climatic conditions that you have in here, or at least I found in here. And correct me if I am wrong, probably you have a better, considerations of that, I'm very sure you do. But I'm gonna give you an idea what kind of TMIs we manage in India, all right? And for example, the Rajasthan area that we had in here is about minus 60. And the one that we got in Jaipur, which is, around here, is about minus 30. Is that around here? Okay. And Guwahati is about plus 80 in there. So here we got in a very, very wet region, right? So you got those values in there, and we're going to be using those values to go forward. We're not going to calculate them, but the equations are there for you to use later on and calculate the one for your region or for the soil that you need. Okay, so you got the TMI. Now you need to predict the equilibrium suction under the pavements, right? For that, so you got this one, and you're gonna need some properties of the soil of the project. Remember the thing with the roads, if the road is a longitudinal thing, you're gonna need a lot of soil properties because you're going to need probably miles and miles or kilometers of roads. It's not like a building. So you're going to be analyzing sections of your pavement doing that. Soil properties, you get the matrix suction. So how do you get between TMI and matrix suction? I was telling you, you may have the same sand here or in Rajasthan, and you're going to have different suctions at equilibrium, right? Because the evaporation or precipitation. And we visited about 30 sites within the United States with my good friend, Yasan Ayaki, or also Uganda Pereira. He's from Sri Lanka. And we worked together on this back in 2008. And, we went and actually we cored through the roads, like the same that we did for LTPP. Well, they did for LTPP, we did in here, very carefully coring, not to get water in there. You know that those coring machine gets hot if you don't put water, right? You have to put water in there. Well, we couldn't put water in there. So we have to chisel at the end to get the core out and just, dig for the soil. And it was very nice work, but a lot of work. Spent about a year in the road doing that, all right? Collecting data from this road. And we measured what properties they have. We got Atterberg limits, water contents, the density of the soil, grain size distributions, and we measured the suction that we got. We did it close to cracks of the pavement and away from the cracks because we wanted to be the one at equilibrium, one that we had no water in there, right? To figure that out. And based on that, we got all this data and we created family of curves in which we were able to relate the T01 moisture index. This one was all the way to United States. And I mean, we got all the TMIs available in there, right? And we were able to put all these points in there and calculate the suction value for granular material and for subgrade materials. And that's how we create this family of curves. That was his thesis, Pereira's thesis, and that's how we relate the soil properties to the TMI and the suction of the soil. So it's a little bit different because of the suction. But it's not the soil type, it's the environmental that will change the property. The soil. And we just did very nice work in there. Okay, this one is the model for granular-based materials. And that's or for sand materials, sands with no PI pretty much, or very low PI. And this is the soil for the subgrade material, okay, higher PI. And they were a function of passing 200 at WPI. So you're going to have in there models to go from TMI to suction. Now you got suction, now you need saltwater characteristic curves, right? You can go to the laboratory and measure them, or you can use, you need the saltwater characteristic curve, right? So you can use this is the saltwater characteristic curve. Those are many, many models. If you do data points in your laboratory, you have many, many models to do the regression analysis from Brooks and Corey all the way to the Friedland equation that are a little bit more complicated. These are the testing that, I'm not going to go through that. We already went through that in this one. And I have here a family of curves for you. Okay. How do you get that one? Well, we use about 1,227,000 soils to do that. How do you get this data? Okay. Well, I went to the National Resources Conservation Service from the U.S. Department of Agriculture. If you figure out the agricultural engineers and the agronomists and all of these have been using suction for 100 years. And that's what we get. Actually, that's what everybody got, the condition of that, right? So basically, we do have, we put together a national catalog of saltwater characteristic curve because that database was created with the then Bureau of Public Roads, and therefore they got all these engineering properties for us in there. That is available online. So you can get, so we went over there, we got the soils. That was a thesis from Torres Hernandez, a great student also of mine. And basically he put together family of the same kind of soils depending on the geology that we had in there and on that. So with that, we basically made a catalog with about 32,000 plastic soils and about 4,500 non-plastic soils. And we create family of curves. That one actually was my thesis, the first family of curves that was available. And then he modified those with a mine was with about 300 soils that I got from the Murray Friedland. And this one was, 36,000 soils. So this is a great family. And then you got the saltwater characteristic curve for different, this is the plastic soil material, this is the granular-based materials as a function of the D10 of the soil, okay? So you're gonna need what? Grain size distribution in here. You're gonna need passing 200 and PI to get that. So you can use those ones instead of reading, or just if you have laboratory data, then you use that, right? You use that. And then we got now the suction, and now we can, the moisture content, and now we can relate it to the environmental factor, right? And that's the model that I show you in the morning. This is the model that is being used by the design guide. It has only two categories, one for fine-grained materials and another one for coarse-grained materials. And the other one is the model that was put together by Kerry in 2010, one of my great also PhD students. And basically you can see how the environmental factor changes for clay materials, for granular materials, below, dry of optimum or wet of optimum, right? So you got this model in there. There are equations, but you can use the graph as well, just to get that the approximated value. I just put a big picture so you can just enter that easily, right? All right, so you get the stiffness of the material by calculating this one, modified by resilient modulus. And the typical resilient modulus from the laboratory at optimum condition are given in these tables, right? So I gave you a couple of soils, and you can just have the resilient modulus that we got in the lab that also you learn how to get it, right? And those are pretty much ranges of material that you can use. So the activity is you need to estimate the resilient modulus at equilibrium with these, steps that I've just put together for you. And basically, this is the resilient modulus that the subgrade or the soil will tend to reach during the life of the pavement structure. Use properties for soils D and F. D and F are here. I just took, some soil from, I think, Holtz and Kovac's book or something. All right. So you got that. And this is the grain size distribution for those soils, soil D and F, right here. One is a very sandy material, PI 0. This is the clay material. These are the liquid limit, plastic limit. D is a non-plastic. F is a plastic material. All right. These are the natural moisture content at the Atterberg limits. And here, I gave you saltwater characteristic curves, so you don't have to use my curves, right? So you can use those guys. Those are measured data for this thing. And there is all D and volumetric water content versus suction, and D and F. But now if I give this one, I put you to do the whole regression analysis, right? How much, Dr. Barat, how much effort they need to put on the final exam? Little effort or a lot of effort? All right, let's, yeah. Yeah, because this one might very well be a final exam. Oh, yeah, they need to do that, okay, right. So no, the examiner, so we're gonna do something, because it's gonna be a tutorial, it's gonna be doing that. You're not gonna use the saltwater characteristic data. You're gonna be using the PI information you got and the passing 200 you got, and you're gonna estimate based on the correlation of the equation, right? Why? Because if you don't do that, you're gonna have to do the solver to do a regression analysis, right? And I don't want you to do that. It's a lot of work. Well, for a tutorial. All right. So you report the suction at equilibrium. You report the degree of saturation, resilient modulus at optimum, and the resilient modulus at equilibrium, right? It's pretty simple. Are 4 equations that you need to follow. Okay, so we're gonna have in here the data, and we're gonna have the first 2 rows in here. So 6 people in here doing soil D and Guwahati. All right? The last 2 rows and the last row that you have over there, we're going to be doing soil D in Jaipur. That's terrible. Okay, so then we got 1, 2, 3, 4 rows. The last, rows, we got 1, 2, 3, 4, 7 people there. We're gonna do the soil F in Guwahati, and the first 2 rows in here, you guys gonna do soil F in Jaipur. All right? So everybody okay with that? And I'm gonna be here. I don't know if you guys wanna do this right now, or you guys wanna do this during the evening, rest, and come here and report in that. Probably we're gonna do that. Yeah. So what time it is? 4:50. We're gonna come back tomorrow, and basically I want you to just do the table, right? Fill it up, whatever you got, okay, in the table, and it's gonna be so fun to see what the numbers are gonna be. Okay, can I work together with it? Yeah, you can work together. It's fine, okay? It's fine. I just want you to learn and go through the system and see.
Guys from the same city, right?
Huh?
Guys from the same city?
No. Whatever that, yeah. Are you guys the same city? Oh, here we go.
Same city, like Guwahati, Jaipur.
Yeah, exactly. Yeah. And the soil, yeah, like the one I divided, yeah. You can work together on that. Now, another thing is we can report that tomorrow in here and see what you get, okay? And if you have any question, I want you to make assumptions, okay? If I said, okay, there is some missing information in here or something like, go ahead and make an assumption. I said, I assume this. See what you get. I don't think you have many things to assume in there, but if you need anything, just be resourceful. Okay? All right, guys. You got any questions? Do you got this material with you?
Yes.
You do? Okay, the last tutorial on that? All right. So you got the material, you got everything? Okay. Yes?
We need to discuss the coupled effect of traffic on resident.
The effect of traffic. Yes, we did. We did, but I'm going. Okay, so where is the effect of traffic on the resilient modules? And the resilient modulus are optimum, right? When you do the resilient modulus at optimum, what we look at this morning was that you have a stress sequencing, right? And you do a dynamic loading that is Haber sign, okay? That resilient modulus that you get in the lab is actually what represents the response of your material due to the traffic. So,
Like we are doing the test at different sequence, different company pressures and stress that is occurred. So at what company pressure should I take the result?
well, at the stress condition that you're going to have in the field. Okay.
Based on the payment thickness and
Exactly. So you're going to have a payment thickness. You're going to have, well, I didn't go there. This is payment design. That is not my forte. But basically, what you do is you take all these stress conditions that you have, and they're going to be low, medium, or high volume roads, on this one. And you're going to know what are going to be the deviator stress and the confining stress that you're going to need for that.
at a given set
Exactly.
at the top of subgrade layer.
On the top of the subgrade layer, exactly. And that's how you choose, based on that family of the resilient modulus that you get, which one is the one that you're going to be using for your conditions. That's exactly right. Okay. So, yes, you're going to need the number of repetitions that you're going to have in the road, and you're going to need figure out how, with that number of repetitions, what is the resilient modulus? I think it's with the stress state condition that you have. I don't have that information for you, but that's how you get that one. You get the stress conditions in the field, and then you use them to calculate what is the resilient module you're going to find for that. Okay.
As an input, I think we have to give a trial modulus for each of the layer on the design modulus.
Yes. So this resilient modulus at optimum is done for the granular based material, for the subgrade material, and for the subbase and subgrade material. So you get that one. And all of them are going to have the stress conditions that are in the field. Mhm. I'm just trying to figure out how to relate this one to the number of repetitions.
Online people
Oh, what happened?
question because it's
Oh, question.
their assignment. Okay.
Oh, do we have any other parameters similar to TMI for freeze-thaw cycles? Yes, we do. The thing is, I didn't bring that in here. Okay, so here is what we do, Emad, but unfortunately, I didn't bring it in here. But let's see if I can do that. What in reality, these are the, oops. We got the granular, the asphalt pavement, AC, the granular material, granular base. And let's say you got no sub-base, but you have the subgrade in here, right? So you have those soils in here, and basically we are calculating the TMI every month. So, and for every, we divided actually the subgrade into, you can divide it into different sublayers, right? Depending on the accuracy that you want to put all the parameters in here. So let's say you do have those. AC, obviously, there is no flow through here. But then you said, okay, for time equals the first month, month number 1, we calculate that environmental factor, okay? And that's going to be an environmental factor in here for unfrozen condition. And in here, we're going to have an environmental factor for unfrozen, and here too. And actually, depending on the number of sublayers that you have, this is unfrozen. So you're going to be using unfrozen environmental factor of them. You do the same for month 2, 3, 4. Let's say on month number 5, you start getting frozen depth conditions, okay? You calculate the frozen environmental factor in here, the frozen environmental factor in here is unfrozen, unfrozen, and so forth. The next one, it's 6 months, and so forth. And you're going to see the front of here going up and down because you calculate the frozen, and some of them are going to start into the thawing condition, and so forth. So you do have that in here, and basically what you find out is for the whole layer, because you're going to need to put this one into your resilient permanent deformation model, rotting models, you're going to have a composite value of what you get in order to figure out what is the condition. Now, the composite value will be with the depth, but with the time, you can have different values, right? So you got, again, the unfrozen environmental condition, the freezing condition, the thawing condition, and the comeback. And I have those, I didn't bring them in here, I just want the unfrozen, but I'm going to dig into my notes on this one, and I'm gonna send you those equations, okay? And the equations are nothing but an empirical modulus or environmental factor when you do have frozen conditions, and an empirical reduction to a point, and an empirical equation in here to recovering depending on the soil type, okay? That's nothing more than that. But this one creates the environmental factors are different frozen and unfrozen conditions, okay? So yes, they are available, and I'm gonna send them to you, Emad, okay? I'm just not gonna use them to this activity. Do you guys understand that? Okay. All right, guys, so class is dismissed. I hope you guys can just spend, a few minutes doing that. 30 minutes or something like that, okay? And I want to see results tomorrow.
Online participants have not been given the assignments.
The what again?
online participants.
So they didn't get the not assigned.
Oh, they didn't get the assignment. So,
They should be under some town, Guwahati, Jaipur, something like under ABC, the class.
oh, no, oh, I see. Okay, how many we got in here? We got 4?
As of now, 4.
All right. Okay, so, Emad. Where is it? I see what I mean. Yeah, okay. What we get? So, Emad, you're going to have soil D for Guwahati. Rohit, you're going to have soil D for Jaipur. Babitra, you're going to have soil F for Guwahati, and it's Srinivasan, you're going to have Jaipur, soil F, okay? Okay. Emad, you're going to have soil D, which is the granular material. Okay, Emad, Guwahati, soil D. Thank you so much. Rohit, we got D, Jaipur. Babitra, soil F, Guwahati, and Srinivasan, soil F, Jaipur. All right. All right, guys. Hope you have a wonderful evening, and the class is dismissed. You may go.